You type a prompt, your brand new application solves this massive logic puzzle right on the fly, and you just feel like an absolute wizard.
Oh, totally. It's pure magic.
Right, it's magic, but then you deploy that magic to, say, 10,000 users, and at the end of the month, you open your cloud dashboard, and your budget is just completely destroyed.
Yeah, that post-deployment sticker shock. It is basically a rite of passage at this point.
It really is. Welcome to the deep dive, by the way. If you're listening to this right now, there's a good chance you're staring at a terminal window or maybe a system architecture diagram, just trying to figure out where it all went wrong.
The honeymoon phase ends the second that first API invoice lands in your inbox, right?
Exactly.
So we're pulling up a chair next to you tonight because today we are tearing down the architecture of AI cost optimization. We're looking at some incredible notes from a series literally titled Running AI Without Going Broke, which is exactly what we need. We are stepping out of the theoretical capabilities of large language models and getting into the really hard engineering discipline of just keeping your startup alive.
Yeah. And the mission tonight is basically the 80-20 rule of AI architecture. We want to find that 20% of engineering effort that's going to slash like 80% off your cloud bill.
Which is massive.
Right. And what's crazy is that the fastest way to stop the bleeding doesn't actually involve switching models or migrating clouds or any of that.
No, not at all. It starts with restricting how much the model actually talks back to you.
Okay, let's unpack this because we're talking about output tokens, right?
Output tokens, yeah. They are, without a doubt, the single most expensive component of an LLM system. Before you optimize literally anything else, controlling the length of the response is the most immediate lever you have.
I always think about it like a database query. Like if you're building a lightweight profile widget, right, and you only need a user ID and an email address, you don't write select from users.
Oh man, no, that's a cardinal sin.
Right. You're pulling down their bio, their login history, you're tying up database memory, choking your network bandwidth, all for data you're going to instantly drop anyway.
Exactly.
Yet when we transition to LLMs, it's like we suddenly forget everything we know about resource efficiency. We just let the model generate 5 paragraphs of polite preamble.
Yeah, that database analogy is perfect, actually, because it gets right down to the hardware bottlenecks. Like with traditional databases, you're worried about network bandwidth and disk I/O.
Right.
But with LLMs, you're worried about VRAM bandwidth. Processing a prompt, the input tokens, is a highly parallelized compute-bound operation.
The GPUs just chew right through it.
They chew through it incredibly fast. But output generation, that is an entirely different beast.
Because it's autoregressive, right? It's generating one token at a time, sequentially.
It has to calculate the attention scores across the entire context window, generate one single token, append that token to the sequence, and then feed the whole thing back into the massive neural network weights just to predict the next token.
Over and over again.
Over and over. It is a memory-bound, computationally agonizing loop. Every single syllable of that polite preamble is locking up GPU cycles.
Wow. So when you ask your system to, say, extract a Boolean from a text string, and the model replies, certainly, I would be absolutely delighted to help you extract that information. Here is the JSON payload. You're paying a premium for a virtual assistant when you just needed a data pipe.
You're paying for the compute time, and you're paying for the memory bandwidth to pass the entire context window through the model's weights for every single one of those useless words.
That's painful to even think about.
It is. Enforcing strict brevity, using system prompts that demand, return only valid JSON, no markdown, absolutely no conversational text. That is foundational cost control.
Okay, so dropping the conversational text stops the immediate hemorrhage. We're returning strict JSON. But I'm looking at the architecture, and even if we've trimmed the output to a handful of tokens, we're still paying a massive premium per token if we're sending that simple JSON extraction to a frontier model like GPT-4 or Claude 3.5 Sonnet.
Right, which leads directly into the architectural layer. Model routing.
Model routing.
Yeah, you stop over-explaining, and then you stop over-hiring for the job.
I love that framing.
If we connect this to the bigger picture, implementing a routing layer to push simple tasks to cheap models and complex tasks to expensive ones, it typically drops total spend by 60 to 80%.
Wait, 60 to 80%? That is insane. It's like pulling your principal engineer off a complex Kubernetes migration just to fix a missing semicolon in a CSS file.
Exactly. You wouldn't do it.
No, it's a massive waste of resources. You give the CSS typo to the summer intern, the intern is perfectly capable, and their compute cost is a fraction of the principal's.
That's exactly it. But building that routing layer introduces a really interesting system design challenge.
Because Because you're trading simplicity for efficiency.
Exactly. You're no longer just calling one single API endpoint. You need an evaluation mechanism, a router, sitting in front of your LLMs to classify the incoming user request.
And that router adds latency. I mean, it's an extra hop in the network. Plus, you have to maintain fallback logic, handle different API schemas, and maybe even host a fast, small classifier model just to make the routing decision in the first place. I can literally hear engineers groaning about the overhead right now.
Yeah, it undeniably adds overhead.
Yeah.
But let's look at the math for a second.
Right.
If your bill is $10,000 a month and a router cuts that down to $2,000,
That's an $8,000 delta.
right, and that $8,000 easily pays for the engineering time required to build and maintain the extra layer.
Yeah, that makes sense.
The router just checks. Does this request require complex multi-step reasoning or deep code generation? If yes, route it to the expensive frontier model. Does it just need basic text summarization, simple translation, or a quick sentiment analysis?
Permit it to the intern.
Yeah, exactly. Route it to an open weights model or a much cheaper Tier 2 API.
Okay, so we've optimized the output length, and we're routing intelligently. The interns handle the easy tickets, the staff engineers handle the architecture.
Right.
But here's where it gets really interesting. What happens when traffic spikes? If 10,000 users ask the intern the exact same simple question, we're still paying the intern 10,000 times.
Which is still a lot of money.
Exactly. We need caching. But traditional caching feels completely inadequate for LLMs.
How so? Walk me through the friction you're seeing.
Well, we're software engineers, right? We love Redis. We memcache everything we possibly can. But a traditional key value store relies on highly predictable queries with exact string matches.
Right.
LLM inputs are chaotic. The state space is practically infinite. One user asks for a summary of a financial report. The next user asks for the same summary but wants it in bullet points.
Yeah.
The third user pastes the same report but adds a typo to the prompt. A strict Redis cache misses all of those. So how much redundant compute are we actually saving in the real world?
That is the exact limitation of traditional caching in this space. And it's why modern AI architectures split this into two distinct mechanisms.
Okay, what are they?
Response caching and prompt caching. They solve entirely different problems. Let's tackle response caching first, which addresses your chaotic user scenario. You don't use strict string matching. You use semantic caching.
Right, so we're comparing the mathematical embeddings of the incoming question to previous questions.
Exactly. You compute the vector embedding of the new user's prompt, and you run a fast cosine similarity search against your cache.
Okay.
If the new prompt is, say, a 95% semantic match to a question you answered 5 minutes ago, you don't even wake up the LLM. You just return the cached output.
And just like that, we completely bypass the autoregressive output generation we talked about earlier. Zero LLM compute costs, practically zero latency.
It's beautiful. But semantic caching has a massive blind spot.
What's that?
Well, if your similarity threshold is too loose, you serve the wrong answer. Like the user asked for bullet points and you gave them paragraphs. But if it's too tight, you never get a cache hit. That's where the second mechanism, prompt caching, completely changes the math, especially for retrieval augmented generation, or RAG systems.
Oh, this is where it gets incredibly cool. Because with RAG, we're constantly injecting massive context windows like a 10,000-word company manual into the system prompt just to ground the model's domain knowledge.
Exactly. And processing those 10,000 input tokens requires the model to compute the key value cache.
The KV cache.
Right. The KV cache is the mathematical representation of all those tokens. It's the attention scores that the model needs to actually understand the context.
Yeah.
If 10 different users ask completely different questions about that same manual, semantic caching won't help you at all. The questions are different.
So without prompt caching, the infrastructure recomputes the math for that massive 10,000-word manual 10 separate times. We're just throwing parallel compute cycles into the void.
It is staggering inefficiency. But prompt caching solves this at the infrastructure level. It stores the pre-computed mathematical state, the KV cache, of that massive static system prompt right in the GPU's VRAM.
Wow.
Yeah. So when the next user queries the manual, the system only has to compute the attention scores for the handful of tokens in their specific unique question. The heavy lifting for the 10,000 words is already done.
Okay, I want to pause here and look at where we stand, because we've covered a lot of ground.
We have.
We're enforcing strict JSON to kill verbose output. We've
Ugh.
built an intelligent router. We're semantically caching identical questions, and we're prompt caching our massive RAG context windows. We have basically squeezed every drop of efficiency out of our API usage.
Absolutely.
But let's play devil's advocate. Let's say the product is a massive hit. Traffic is exploding. I'm looking at my AWS bill right now, and my API spend is hitting $15,000 a month. Renting a rack of dedicated A100 GPUs and self-hosting, say, Llama 3, is starting to look really tempting. Tell me why pulling the plug on third-party APIs is a terrible idea.
Well, this raises an important question. It's not inherently a terrible idea, but you have to look way beyond the hardware bill.
Right.
The industry break-even point for moving from API usage to self-hosting generally sits between $5,000 and $20,000 a month in API spend.
Okay.
But that number is a trap if you don't factor in the MLOps tax.
Ah, the total cost of ownership. Because spinning up a GPU instance isn't like spinning up a Postgres database.
Not even remotely. You're dealing with continuous batching. You're fighting with VLLM or TensorArt LLM just to get your inference speeds up to par with Anthropic or OpenAI.
Yeah, that sounds painful.
It is. You're managing VRAM fragmentation. You're dealing with out-of-memory errors that crash your entire container in the middle of the night just because one user sent a prompt that was slightly too long.
Oh, and don't forget NVIDIA drivers updating and breaking your entire PyTorch environment.
Exactly. So you have to ask yourself, if you're saving $8,000 a month on your API bill, but you have to hire a dedicated machine learning operations engineer for $160,000 a year just to keep the inference servers from catching fire, did you actually save any money?
You definitely lost money. And more critically, you lost engineering velocity.
Yes. The complexity of self-hosting at scale is immense. Your core product engineers are suddenly spending their sprints debugging GPU kernel panics instead of shipping actual features.
That's the real cost right there.
That's exactly why that $5,000 to $20,000 threshold exists. Below $5,000, self-hosting is an absolute distraction. Just let the API providers manage the bare metal physics.
But as you cross into that $15,000 to $20,000 territory, the calculus shifts, right?
It does.
If you have highly predictable, sustained traffic, not spiky, unpredictable bursts, but steady load, renting a dedicated GPU instance starts to make mathematical sense. Because you can run that hardware at 90% utilization around the clock.
Right. At that point, it transitions from an API optimization problem to an infrastructure optimization problem. It becomes a serious architectural leap that requires a dedicated strategy meeting, not just, a rogue engineer spinning up an EC2 instance on a Friday afternoon.
Which brings us to the overarching reality of all this. The 80-20 rule of AI cost optimization gives us a highly actionable playbook.
It really does.
If you want the vast majority of achievable savings, you don't jump straight to self-hosting. You focus on the 3 pillars we unpacked. First, output length control. Start paying for the auto-regressive polite preamble.
Yes.
Second, model routing. Stop assigning your principal engineers to do the intern's job. And third, caching. Stop paying to recompute the exact same matrix states over and over again.
Master those 3 domains and you fundamentally transform the unit economics of your application. But, getting the bill down is only half the battle.
What do you mean?
Because the secondary consequence of all this hyper-optimization is what happens in production over time. According to the source material, a perfectly cost-optimized system can degrade silently.
Silent degradation. Wow. That is a chilling concept for anyone maintaining a production system.
Oh yeah, it's the stuff of nightmares.
And it leaves us with a really fascinating tension to think about. If you've aggressively shortened your model outputs, and you've routed a massive percentage of your tasks to the absolute cheapest models available, and you've heavily cached all your historical answers, does hyper-optimization actually make your system brittle?
It creates a massive vulnerability to drift.
Think about it. By locking down the variance to save money, are you blinding your system to subtle shifts in what your users actually want?
Right.
If a user asks a genuinely novel question, but your semantic cache is tuned just a little too aggressively, it might serve them an outdated generic response.
Or if the cheapest open source model handles the query to save fractions of a cent, it might miss a crucial nuance, right? Or hallucinated detail that the expensive frontier model would have caught immediately.
Exactly. You've optimized the budget perfectly, but you might be silently degrading the resilience and the quality of the product in the real world.
It's the ultimate tightrope walk. It's the tension between the finance department's spreadsheet and the system's actual architectural integrity.
It's a trade-off that doesn't show up on a cloud bill, but it definitely shows up in user churn. And that is definitely something to chew on during your next code review.